So thank you all for coming to this talk, and Ashok, thanks for introducing me. I'm going to tell you today about a model for text documents, which we call a hidden topic Markov model. And I'll just say that this is a joint work with Mikhail Rosenzweig, who was a postdoc at Hebrew University at the time we did this work, and with Yair Weiss, who is a professor at Hebrew University and is also my PhD advisor. And this work has been published in AI Stats. So let's begin. I will start with an introduction, telling you a little bit about problems related to text documents. I'll define the problem of latent semantic analysis that we want to solve, and I will review a little bit hierarchical models for text documents. Then I will present the HTMM, our model. HTMM stands for Hidden Topic Markov Model. Then, after presenting the model, I will describe an EM algorithm for learning in this model, meaning to estimate the parameters of the model. And then I will show you some results. We really have cool results, so it's worth waiting to the end. And I'll summarize. OK, so there's many computers today, and there are many texts out there, and there are many things that we might want to do with text. One of them is information retrieval, which is really something I don't need to talk about here at Google. You know about it much more than me. We have some query, we have a set of documents, and we want to retrieve the documents that are most relevant to this query. Another problem we may think of is automatic classification and organization of texts. One example is when we get an email, it will certainly be useful if some automatic tool will decide whether it is a spam email or whether it is something that we actually want to read. Another thing that could be handy is if the emails that we receive will fall into folders automatically without us having predefined explicit and exact rules for each email to map into a certain folder. Another thing that could be nice is topical segmentation. If we have a long text that discusses several topics, it could be nice if we can just partition the text according to the topics that are being discussed. This also relates to summarization of documents. Maybe if we could partition a document into several sections, then we can summarize and find some keywords that represent each section. And there is also the task of automatic translation, which is very hot here. Again, something you know about much more than I do. And there are many other tasks that we can think of. And something that is related to all the tasks that I've mentioned is that if we can somehow capture the semantics of the document, if we can somehow really figure out what this topic is talking about, it might be helpful to perform each one of these tasks. So let's say what we mean by semantic analysis of text documents. So I have a set of text documents. And I want to figure out what these documents are actually talking about. This means that I want to associate with each document several topics that the topic deals with. A topic can deal with more than one. A document can deal with more than one topic. For example, if we have an interview with the president, he might talk about foreign affairs, then he might talk about economy, then maybe about some other domestic issues. So it may be more than one. It may be more than one topic in a single document. And we also want to figure out what's the meaning of the words that we see in the corpus that we have. We want to assign each word to different topics, and keep in mind that a word can have several meanings, and it can be related to more than one topic as well. If we take the word bank, for example, then it can be the river bank, or it can be the place where we put our money. So we have these two problems. We want to assign a mixture of topics to documents, meaning that we want to assign probability of a topic to each document. This will also tell us what is the proportion of this topic within the document. And we want to do the same thing for the words that we see in the corpus. The problem that we're talking about is totally unsupervised, which means that our input is only a set of documents. There are no labels. No one tells us anything about the relation between these documents or between different words, and we don't know what are the topics that we are actually looking for. So topics are not predefined. I don't know to tell you ahead of time what are the topics that I'm going to find. And after I perform this semantic analysis, only then I can see what are these topics by inspecting the words associated with each topic. That's how I'll figure out what are the topics that I found and see if it's meaningful or not. However, I do have to, in my work, I do have to specify how many topics I'm expecting to have. There are other works that discuss this issue and tell how to find the best number of topics in some sense. So there has been a vast amount of work about semantic analysis in text documents, and it will be impossible even mention all the works, so I'm not going to try to. I will only mention a few works that are related to mine. So roughly speaking, you can talk about an approach in models for text documents that is called bag of words. The bag of words approach represent each document as a count of the number of words that appear in these documents. That means that you take the corpus that you have, and then you pre-process your text documents. You count how many times each word appears in each document. And after you counted the number of occurrences of words in the document, you discard the document, and all you keep is the number of words, is the counts of words that appeared in this certain document. So usually a document can contain only a small number of words from the entire vocabulary. So this is a sparse representation of the text document, which is quite efficient. You don't have to keep all the original data. You have a compact and sparse representation. However, you lose a lot of information by with this representation, because you no longer have the structure of the document, and you don't see what are the relationships between words within the document. So there is a work from the beginning of the 90s called Latent Semantic Analysis, or LSA, that started with this pre-processing. They built metrics of document term per occurrence, and then they used tools of linear algebra, SPD, singular variable decomposition, to map documents into the space of topics, and they did the same for words. Later on, in the end of the 90s, there is a work of Thomas Hoffman called Probabilistic Latent Semantic Analysis, in which he presented a graphical model, a statistical graphical model, that describes a generative model to create the documents in the corpus. I'm going to get into this work in details. And a few years later, David Blair and his co-authors presented a work called Latent Dirichlet Allocation, or LDA. They introduced Dirichlet priors to tie together parameters of different documents. I will also describe this work in more details. And there are many extensions to the LDA work. For example, there is a work of Mikhail Rosenzweig and collaborators about how to incorporate author information into the semantic analysis, and there are many works that incorporate other sources of information. There's another work that builds on the LDA that integrates syntax information into the semantic analysis, which is a hidden Markov model to represent the syntactic dynamics over the documents. So the last work is not a bag of words model, because it really has to follow the entire document to see what's going on in terms of syntax. So my work is not a bag of words model, and the main motivation is that when you have a text document, then usually text documents tend to be coherent. When a person speaks or writes a document, it doesn't just randomly pick words to talk about. Usually, if you say something, then two words that are next to each other are related in some way. And it will be a shame to ignore this information, which is what we do when we use the bag of words representation. Because once we discard the original documents, we have no way to know what was the distance between two words. We can never know if two words were adjacent to each other. So the main motivation for my work is to keep the original document, and then somehow to use the information that we have from the adjacency of words or of sentences. And because we keep the original document and we don't just count the number of appearances of words within this document, we have an explicit representation for each instance of word that we actually see in the document. So we can distinguish between different instances of the same word, something that appear in the same document, something that is impossible in models that just count together all the instances of all the appearances of a word within a document. And then you no longer have a way to figure out what's the difference between two instances of the same word according to the context. So that's the main motivation. My work builds on LDA and on probabilistic latent semantic analysis, so I will describe these works in details before I'll get to my work. So the probabilistic latent semantic analysis, which is also called the aspect model, presents a generative model of how to generate the corpus that we see. This means that I have to tell you how to generate each word in each document. And this is described with a probabilistic process. If I want to generate the word W in document D, so first I want to pick the document. So I pick a document D with a certain probability. After I've chosen the document and I want to generate the word, I have to decide first what is the topic that I want to talk about. So after I've chosen the document, I pick a topic associated with this document that is drawn from a distribution, a multinomial distribution that is associated with the document. We denote this distribution by the vector theta. It is a vector of probabilities associated to the document D, and each one of the possible topics that we denote by Z has a certain probability. And after we decide what is the topic we're going to talk about, we choose a certain word that relates to this topic, and each word has a probability to come from this topic. So for each topic Z, we have a vector of probabilities phi, and phi Z of W is the probability to generate the word W after we have chosen the topic C. We can describe this generative process with a graphical model. First of all, there is a disclaimer. That's not the way that Hoffman presented the graphical model in his work, but it is equivalent. So I don't know if everybody here is familiar with graphical models. So I'll say a few words about what this picture actually says. So we have random variables that are inside circles. For example, this is phi, which is well, that's not a good example. Let's take Z. Z is the topic. It's a random variable. So it is inside a circle. And the errors between the circles represent conditional probabilities. When I have an error from theta to Z, it means that Z depends on theta. In this generative model, theta and phi are considered as parameters and not as random variables, but I'm writing it this way because that's the way we will treat these parameters later on in this talk. So if I want to describe the generative process that I showed you in the previous slide using graphical model, what I say is that for each document, I have to generate a theta. After I have this theta, for each word, I have to draw Z randomly from the distribution theta. And after I've chosen Z, I pick a word W from the distribution phi that is specified by Z. So again, theta is the mixture of topics that are assigned to a certain document. Z is the topic that I pick for a certain word. W is the word that I generate from this topic. W is shaded here because it is observed and we know the value of W. We don't know the value of any one of the other variables. And phi is a vector of probabilities that are associated to the topics, and they tell us what is the probability to generate each word after we have chosen the topic. There are also the rectangles in this picture, and the rectangles, which are called plates, represent repetitions. In the process that I showed you in the previous slide, we describe how to generate all the words in all the documents that we have. So This inner plate represents how to generate all the words within a certain document. So within a document, I have a single theta, and then I repeat the process of picking a topic and picking a word n times, where n is the length of this document. And I repeat this whole thing d times for d documents in the corpus, so that's the outer plate. And I also have many topics. If I have k topics in my analysis, then I have k probability vectors phi, so that's why I have the plate around phi. So the difference between this representation and the way that Hoffman presented his work is that the way Hoffman presented his work, there is a random variable d associated with the document, and theta and phi are actually parameters. But I'm going to keep this representation because that's the way we're going to see it in the rest of the talk. Then after Hoffman presented his model, he suggested to use an EM algorithm for learning in this model. This means for estimating the parameters theta and phi. And the EM algorithm had a problem of overfitting. Then he suggested a tempered EM algorithm, and I'm not going to get to any more details. A few years later, David Bay suggested the Latent Dirichlet Allocation model, which ties together parameters of different documents to overcome the overfitting and to have a more consistent probabilistic model. So I'll skip the verbal description. I'll just go to the graphical model. So in the previous graphical model that we had, we didn't have these parameters beta and alpha. The main difference between this work and the work of Thomas Hoffman is that we now consider the parameters theta and phi not as parameters but as random variables. That means that there is a prior placed on these variables. They come from a certain distribution. So by relating these variables into to a certain distribution, which is common to all the thetas, we actually tie together thetas of different documents, and then we have a more consistent way to describe our corpus. And this also helps us to cope with the overfitting problem. So if you want to we need to specify a certain distribution over the thetas. So a natural choice is going to be the Dirichlet distribution, because the Dirichlet distribution generates probability vectors, and from the mathematical point of view, the Dirichlet distribution is conjugate to the multinomial distribution, which makes all the math much more simple. I can say in a few words that when I said that the Dirichlet is conjugate to the multinomial distribution, this means that if you take the posterior probability of theta, where z is multinomial coming from theta and alpha is a Dirichlet pair, it means that the posterior distribution of theta is going also to be multinomial, which makes everything simpler. So the specific, the main idea is just to tie together all the parameters using some pairs on the parameters. So in a similar way, we have the betas that are Dirichlet pairs on the probability vectors phi. And in this way, we just make some relation. We make a strong relation between different documents. Then the algorithm that was suggested in the LDA paper was to use variational EM. Nowadays, there are also other approaches. There are approaches of collapsed Gibbs sampling to the LDA model and to works that build on it. And there are several options of how to do inference in these models. So in the previous slide, I used again the plates notation, which I remind you means that we just repeat over and over again the process of generating a word inside the document. I can unwrap this representation and write explicitly the way that a document is generated. In this way, where this model is exactly the same as the previous one, I just unwrap the inner plate, and I have the sets of words and topics one next to the other. And you can see that there is no direct connection between the topics of different words inside the document. this is exactly the problem that we want to solve in my work. We want to relate different words inside the same document. So in the HTMM, in the hidden topic Markov model, we say that, as I said in the introduction, documents tend to be coherent in some way. If I have two consecutive words or two consecutive sentences, there is a very good chance that these words or sentences actually deal with the same topic. So I said that two adjacent sentences have the same topic with high probability, which I denote by 1 minus epsilon. But from time to time, we do have topic transitions within the document, but this doesn't happen too often. So we said that this happens with a low probability, which we denote by epsilon. And we want to represent these assumptions about the coherence of the document using a Markov chain. So I'm going to represent a document with a Markov chain over the topics and say that with high probability, two topics of consecutive words is going to be the same, and with low probability, it's going to be different. Since I'm keeping the original representation of the document with the structure of this document, I now have an explicit representation of each appearance of each word. So I can now try to figure out what is the meaning of a certain word from the context of this word. So if I want to describe the generative model, first of all, I have to draw the parameters same as in the LDA, but that's not the focus of my talk. And then when I get to create words inside a document, for each document, first of all, I have to choose the topic of this word. So I have a variable psi, which says when I want to generate a next topic, whether it is going to be the same as the previous topic or is it going to be something new. So the first stage is to decide if psi is going to be 0 or 1, if I'm going to draw a new topic or to copy the previous one. And this is drawn from a binomial distribution with the parameter epsilon. With very low probability, I'm going to change the topic. Otherwise, I'm going to keep the same topic. So with high probability, I simply copy the topic of the previous word. And otherwise, I pick a new topic, which comes from the distribution of topics in this document, from the theta. After I've chosen the topic of the word, then in this way, we describe how to create sentences where all the words within a sentence have the same topic. So after I've chosen a topic for a sentence, I have to generate each one of the words in this sentence. So for each one of the words, I just draw a word from multinomial specified by the topic that I have chosen in the previous stage. So WI comes from the phi that is corresponding to the topic that I just chose. If we want to look at the picture of this document, we now remember how the LDA unwrapped looked like. I'll show you the previous picture. That's the unwrapped LDA. So the main difference is that now we put links between these nodes. We'll relate them because we say that the topic of the n word depends on the topic of the n-1 word. So that's the red arrows, and that's the main point of this work. In order to perform inference and to define a consistent probabilistic model, we also have some other variables, the psi's that tell us whether I'm going to simply copy the topic of the previous word or not, or whether I'm going to draw a new one. And these psi's are drawn from a binomial distribution with the parameter epsilon. So again, the generative model is first of all create the first topic in the document from the distribution theta. I always draw a new topic for the first word. Then when I want to generate the second word, then I have to decide if I'm going simply to copy the previous topic or to generate a new one. To decide this, I have to draw a variable psi, which is 0 with a high probability, 1 minus epsilon and 1 with probability epsilon. If psi is 0, I just copy the previous topic. If psi is 1, I generate a new topic from theta. So that's the way topics are generated. So we have this Markov chain that describes the dynamics of topics within the document. And we now have explicit representation of each word in the document, whereas in the previous models, these words were not actually the instances of words that appear in the document. They were only the terms that appeared in the document associated with counts. So now, once I have this model, I can ask a few questions. One question is, what is the topic associated with each word? This could be useful if I want to do topical segmentation of a document, because then I can see if this, I can see what are the topics that I obtained, and just look for the places where there is a transition in the topic of the document, and say up to it is one segment, and from this point and on it is a different segment, and so on. I'm going to show you some examples for that. So maybe it's going to be, maybe it will be better explained with the examples. Another question that I can ask, suppose that I want to do some translation and I see a word that has several meanings, and I'm not sure which one is the meaning that is the meaning of the word of this instance, and I don't know exactly how to translate it. So then I can maybe inspect the topic that I found and choose the appropriate translation according to the topic that I found. Another question that we may ask is, if I want to do information retrieval, maybe I want to know what are the topics that a document talks about. And this is actually captured within the parameter theta that tells me what are the proportions of the topics within the document. The topics themselves are represented by these probability vectors phi that specify what's the probability of each word to come from a certain topic. So if I want to figure out what's the topic that I got, I can just see what are the most probable words that are associated with this topic. So this model allows us to answer many questions. And the algorithmic question is how to find all these variables, how to do inference in this model. So like in the previous models, exact inference is intractable. That's why we have to consider alternatives for approximate inference. And we actually derived two algorithms for approximate inference in this model. One of them is collapsed Gibbs sampling, where we sample the discrete variables, which are the z's and the psi's, and we integrate over the other variables. And the other option, which is what I'm going to focus on, is the EM algorithm that is quite similar to the EM algorithm in previous works, only that we have the inference in the Markov chain. So very briefly, the EM algorithm is an iterative algorithm that it's an iterative algorithm that distinguishes between two sets of variables. It has its latent variables over which we average, and it has parameters for which we find map estimators. And in our work, we have chosen the parameters to be theta, phi, and epsilon, and the latent variables are the z and the psi's. The result that we get from the EM algorithm is the map estimation for the parameters, and we have a distribution over the latent variables. I won't get into the details. I'll just say that the EM algorithm is very straightforward. The E step consists of forward-backward algorithm, and the M step. For the M step, we have closed form formulas, and the details are really not that important and interesting. And I'll just show you some results. That's the interesting part of the talk. So what I'm showing you here is a part of a text document. I trained my algorithm on a set of documents that are papers that were published in NIPS, a conference of machine learning and neuroscience, and I performed the semantic analysis. here I want to show you what are the topics that I found. So I have a section from the beginning of a paper, and I have a section from the end of the paper. This is the abstract that appears in the beginning of the paper, and that's the end of the discussion, and then the acknowledgements and the references. And the colors that you see in this picture correspond to the topics that we found. Words that are colored with the same color were assigned to the same topic, whereas different colors represent different topics. So if we start reading the abstract, we see that it discusses something mathematical. It talks actually about support vector machines. So our algorithm just figured out that all these words correspond to the same topics, and it assigned to all of them the same topic, the same color. This section keeps on going. I didn't cut all of it, but it keeps on within the same document. If you now take a look at the end of the paper, even though there were several topic transitions within the document, you can see that the end of the discussion, which is also related to the support vector machines, was also assigned exactly the same topic. That's why it is colored with the same topic. If you want to see what is this topic, then here I have the list of 20 words with the highest probability to come from this topic. And you can actually see that this word represents something mathematical. It actually captures the topic of support vector machines. You see the word vector, you see the word kernel, you see other words that are related to it. Support, there is also linear separation, and all this stuff that is that's really related to support vector machines. If we continue looking at the end of the document, we see that at the place where the discussion ended and the acknowledgements began, our algorithm managed to find that there was a topic transition, and it assigned the acknowledgement section a new topic. And that's without defining any rules for it. It was found automatically. So we see that this section has the red color. And if we want to see what are the most probable words for the red color, we see that these words are actually related to acknowledgements. You see twice the word acknowledgements with different spellings, maybe even 3 times. You see other words that are related to this topic, such as research, grant, all the institutions that give you the grant, the NSF, you see Institute, Naval, and so on. So it's really nice that we could capture the topic of acknowledgements, even though it appears in only some of these documents. Not all of them have acknowledgements. And it's a very short section within the documents. It's only 1 line. Still, we managed to capture it. Now, if we take a look on the next section, we see that once the references started, then a new topic has been assigned, the green one. And if we take a look to see what's the green topic, then we see that there are names of publishers like Springer, York, Verilog, and other ones. You see, if you keep looking, you see names of people that published. For example, there is Vapnik. You see names of journals, and you can see the word press, and so on. And this topic was also captured just because it consists of consecutive parts. If we continue inspecting this example, you can also see that the word support appears 3 times in the beginning of the document in the abstract, and all the appearances of the word support in the beginning of the document are part of the term support vector. On the other hand, in the end of the document, we also have the word support, but here it has a total different meaning. Here, it is a mathematical term related to support vector machines, whereas here, the word support means the financial help that the authors received from in this case, from Lucent. So we see, if we check what are the topics of the words, we see that in the first case, all the 3 occurrences of the word support were assigned to a mathematical topic. On the other hand, if we check what's the topic of the last occurrence of support within the acknowledgement section, then this one was assigned to the acknowledgements topics. So we see a nice example for partitioning a text into segments according to topics, and for words as disambiguation. Of course, this is only an example. It's not quantitative. I'm going to get to quantitative results as well. I showed you some of the topics that we have. There are also other topics, and they look very nice. But I must say that if you just look at words that represent topics, then the topics that you get from LDA or PLSA also look very nice. So we need some quantitative way to compare the works. However, this example that you see here for the segmentation for the word sense disambiguation is a task that the previous models could not tackle, whereas we can. If I will show you the results of LDA for the same section, these are the results that you see. You don't see segments, you don't see sections that all have the same color. Here, more than 4 colors were assigned to words in the different sections. So I just show you the four most frequent topics that we had in these sections, and the black words are not all assigned to the same topic. These are just words that were assigned to topics different than the ones I've showed you. So you can see that in the LDA, I don't know if it's readable with these colors, but here it's the word sans that has the same color as the word unique and as the word, at least from where I'm standing, it's hard to read. There is a mixture of mathematical terms and of other things that are not related to math. And you can see that all the 4 occurrences of the word support actually were assigned the same topic. So we cannot distinguish between the different instances of the word support within the same document. However, if you do take a look at the most probable words of the LDA, it also looks very nice. But it's just not suitable for the tasks of segmenting a text and for word sense disambiguation. So these are very nice results, but it's not something quantitative, and it can't really serve as a baseline it can't really serve as a measure to compare different algorithms, and we need something quantitative to show you. I'll just say that if you want to take a look at all the results that I showed you were obtained with training a set of I don't remember the exact number. I think it was 1,500 and something documents from the NIPS corpus with 100 topics. If you want to see all the 100 topics, they're all available on the web. So you can see it all and not just the topics that I picked for demonstration. And you can also compare it to the LDA topics. However, we want to have some quantitative measure to compare the two, to compare the different algorithms. And one common such quantity is a quantity called perplexity that captures the difficulty of predicting an unseen part of a new document after we have learned the parameters of the model from a training set and after we have seen the beginning of the document. So the perplexity captures the difficulty of a problem, and the better we learn, the perplexity is going to be lower. So we want to have lower perplexity. In this graph, I show you the perplexity of 3 models with respect to different number of observed words. I see a certain number of words in the beginning of a new document, and then I compute the perplexity for the rest of the document. So as I see more and more words from the beginning of the document, the task is getting easier. That's why the perplexity is decreasing. And in these 3 graphs, I show you the perplexity of LDA versus the perplexity of 2 versions of the HTMM. So the LDA works on different words, and as it sees more and more words, it gets better. The perplexity gets low very rapidly. Whereas in our model, the perplexity is lower all the time, but it goes down very slowly. And the reason for that is that in our model, once you see the topic of a certain word, then you induce a very high probability on the topics of the next words, and you don't get that much from seeing the next words. That's why the perplexity is going down, but very, very slowly. That's the difference between the slopes of the LDA. So we see that if we just see a few words in the document, the perplexity of our model is much lower than the perplexity of the LDA. But as we keep going and we see more and more words, the models are getting closer to each other. Still, the HTMM has lower perplexity, but the difference here is not very significant. Yes?
You really mean by 0, 0?
You can.
You don't see anything?
Yes, you can predict something without having seen anything.
Yeah.
Yes.
But, you don't know the topic? You already predict almost?
You have some association. Because it's a different model. You assign a different probability. If you, with the HTMM, you're going to have a better probability for something that says that the topics are going to be similar along the words of the documents, whereas in the LDA you don't have that. So even if you don't see anything, you still get different probabilities for the two models. And keep in mind that you also learned the parameters of the corpus previously with different models. So the estimations that you have for these parameters are different. And if one of them captures better the parameters of the models, then it's going to influence these probabilities.
So is also the point there that you're, at the beginning of the document, you're just drawing data unconditionally, and that's where you get also...
Actually, what we do to compute the perplexity, we run the same inference on the beginning of the document, and then you get some estimation. When you see no words, then you actually draw a theta for the new document from the Dirichlet pair, and that's what you work with for the rest of the document. Otherwise, you just run the same inference that you had for all the documents, but you fix the parameters. You fix the parameters that you learned from the train set, that is the phi and the epsilon, and you just estimate the new theta. And after you estimate the new theta for the beginning of the new document, then you compute the probability of the unseen part of the document. Other questions? Okay, so I told you that I compare here two versions of the HTMM, and actually in our implementation of the HTMM, we didn't really work on the level of words. We worked in the level of sentences. In our implementation, we said that all the words in the same sentence have the same topic. And this is something that is different from LDA. And we wanted to see if the difference in the perplexity is because of the Markovian assumption or because we simply assign the same topic to all the words within a certain sentence. So in order to check the influence of this assumption, there is a variant of the HTMM, which we call in this slide VHTMM1, which does not assume the Markovian structure on the document, but it works in sentence level. This is actually some sort of sentence level LDA. Because it assumes that the topic of all the words within a sentence is the same, but there is no relation between the topics of adjacent sentences. So that's the perplexity of the VHTMM, and you can see that the perplexity goes down very slow again. That's because if you see a single word from a sentence, you have a very good idea for what the sentence is talking about. And when you see the next words within a sentence, then it doesn't tell you that much. And you see that working in the sentence level improves the perplexity in the beginning, but in the end, it does worse than the LDA and the HTMM. So we conclude that the Markovian assumption really helps to reduce the perplexity, and it's not only working in the sentence level. Another thing we can compare is how the perplexity looks like when we have a varying number of topics. So here we have a fixed number of observed words in the beginning of the new document, and we see the behavior of the perplexity as a function of the number of topics. I should say that in this experiment and the previous experiment, we had a train set which consists of roughly 90% of the data, and the perplexity is average over the remaining 10% of the data. And there's a big variance of the perplexity between different documents, but the results are average of the perplexity. So once again we see a similar picture, the HTMM is always better than the other two versions, and the number of observed words was not it wasn't too big. That's why the LDA does worse than VHTMM. But if you let the algorithm see more and more words, then at a certain stage the picture changes, and then the LDA is better than the VHTMM, but the HTMM is always better than the other two. And an interesting graph is this one, where I show you what are the values of the epsilon that we found from the EM algorithm. I remind you that epsilon is the parameter that tells us how often we actually draw a new topic versus how many times we simply copy the topic of the previous word or the previous sentence. So for my work to have any value, I must have that epsilon is lower than 1, because if it is 1, it just means that each time I draw a new topic, then it's completely equivalent to the previous works that were bag of words works. So here I'll show you the map estimation for epsilon that we obtained from the EM algorithm. And I showed the epsilon that we found as a function of the number of topics. So first of all, we see that epsilon is indeed lower than 1 and significantly lower than 1. And we also see that when the number of topics is small, then epsilon is very small. But as we increase the number of topics, then epsilon is getting bigger all the time. And the reason for that is that the number of topics actually, it says what's the resolution of the topics or what is the granularity. If I have only 5 topics and I run my algorithm on a corpus, which is a set of documents which are research papers, then maybe I will have one topic that is associated with math and another topic associated with neural networks. This is the proceeding of NIPS, so it's neural networks. And maybe I will have another topic associated with other thing that is very common in research papers, but I'm not going to capture the themes within each topic. On the other hand, if I have 100 topics, then each topic can capture a certain theme within a field. Now I have a topic that corresponds to linear algebra and a topic that corresponds to theorems and their proofs, and I have a topic that corresponds to support vector machines, and I have a topic that corresponds to the auditory system of humans, and I have a topic that corresponds to the visual system. I have many topics that correspond to neural networks, and I have topics for acknowledgements, and so on and so on. So if I have only a few topics, then there aren't that many topic transitions, because in the mathematical section, it's all going to be the same topic. But if now I have a certain topic that talks about linear algebra and then something that talks about theorems, then I'm going to have more and more topic transitions, and that's why epsilon is increasing as I increase the number of topics. But still see that, notice that it's always less than 1. Okay, so let's summarize. Then the main motivation for this work and the main claim of this work is that you actually want to keep the original documents and to consider the structure of the documents, because it lets you learn better parameters, better representation. You can actually perform more tasks with your model. So by assuming a Markov structure of document and keeping the original structure of it, we get topics that are inherently different from the topics that you get from LDA. I showed you that we have a topic of acknowledgements. There is no such topic among the 100 topics that were found by LDA, because this is a topic that was found only because it is a certain section within the document, and it doesn't appear that much. So for LDA, it's not very important, but our model managed to capture it. And you can go over all the 100 topics and see that there's nothing like this in the LDA. So we have topics that are inherently different. Remember the picture that I showed you with the colors? This is what the HTMM topics look like. You see that we have contiguous sections that are assigned the same topic, whereas in LDA you have different you have topics that have different meaning. It assigns topics that make sense, but they're just different to certain words within the document. It doesn't create contiguous sections. So I'm not claiming that it is better. I'm only saying that it is different. We also see that having the explicit representation of the text document, we can now, this model is suitable for tasks of topical segmentation and for the task of word sense disambiguation according to the context. And this model builds on the LDA, and it can actually be incorporated with other extensions of the LDA, such as syntax information or author information or other extensions of LDA. All these extensions are orthogonal to each other. So this is just something in addition. And I'll just say one word about the computational complexity of this algorithm versus the previous ones. The main computational difference is that we have an inference in a hidden Markov model in this work, but we have a special form for the transition matrix in this hidden Markov model, and the transition matrix actually depends on a linear number of parameters, linear in number of topics, and not the general quadratic number of terms that you might have in a matrix. And therefore, it is possible to perform the forward-backward algorithm for the inference in the hidden Markov model in linear time and not in quadratic time. So the computational cost of considering the underlying structure of the document is not that high. So it's really something that you pay a little price and you get much more. And I'll be happy to answer questions if anybody else. Yes?
So if you look at your figure 7, the one with the epsilon going up.
This one?
Yeah.
Sure. So it seems like as the number of topics grows, we'll say to say 20,000, the value epsilon is going to go high enough that the actual transition model I can imagine, might be useless.
I think that if the number of topics is equal to the number of words that you have, then you will assign a different topic to each word. And
well, keeping at the sentence level. I mean, so assume that we stay at the sentence level classification, so one topic per sentence. It's never going to happen that we're going to have more topics than there are possible combinations of sentences. But my question is, might we be interested in a different kind of transition model, perhaps moving towards the quadratic number of parameters, which would, you said, make your HTMM inference more complicated?
I agree that it's interesting to check what happens when you have a more general transition matrix, because you want to capture correlations between different topics. For example, if I have the full transition matrix, then I can see that I always have references after acknowledgements, and I can always do something a bit more sophisticated and to see at which place inside a document it happens. And I can use these correlations to say something about relationships between topics, and it can be very helpful for different tasks that we have. But keep in mind that if you have the full transition, it is interesting, but just keep in mind that if you're trying to estimate more parameters, then you need more training data, and the problem is more difficult. And there is also computation cost. So it's definitely interesting, but there was a reason why we did it this way.
But that leads directly to the next question, which is, what do you think is going to happen if we trained on 100,000 or a few million documents versus a couple of thousand?
It's a very good question. I haven't tried, so I don't really know what to tell you.
And with regards to computational overhead, we don't actually have to bump up to the full transition matrix. We could try iteratively adding parameters, so transition between these two topics with this probability, or to any other topic with the remaining probability mass. So in that way, we don't have to use the whole matrix, but we could try to bump up more from this just one epsilon parameter.
You can think of different ways to extend the transition matrix, yet not to have a full one, but I'm not sure if I understand exactly what you're suggesting, but maybe we can talk about it a bit more later.
So, any other questions?
Can you derive can one derive a topic hierarchy or relations between topics? Like have an all-encompassing topic which, breaks down into smaller ones?
So this relates also to the previous question. We don't have in our work, we didn't explicitly represent dependencies and correlations between topics. There is the suggestion of the previous question to have a general transition matrix, not one that is specified by the parameter theta, but one that tells you what's the probability to transit from a certain topic to a different topic. For example, from acknowledgements, you will always move to references, and this captures some kind of correlation between topics. There are also works of other persons. There is the correlated topic models, and actually there were several works about this topic in the last year that have different representation for correlation between topics, and it can be incorporated with this work, but this is not something that we have done in work I presented. These are things we experiment with in different ways, but it's not part of this work.
Is it appropriate to assume that epsilon is going to be constant over the entire corpus? For example, the web probably won't have a constant transition probability.
Of course, it's not constant because different people and different authors tend to do different things. But I think that actually, when I looked at the results that we got, you definitely see differences in the epsilon between different documents. But we specified only a single epsilon. It could be interesting to learn an epsilon per document, but I haven't tried that.
Why didn't you take in the first place not considering the full transition matrix? I mean, in terms of number of parameters, it seems that you already have, for the observation model, you already have number of words times number of topics in the file. So.
That's true that I have a number of topics times number of words, which is way greater than number of topics word. Yet this is very sparse, the phi. So I think that gives you an idea for why you can actually learn it, because the number of words that you have there is the number of words in the vocabulary, and many of them don't even appear in the corpus. So that's the intuitive answer for why you can learn it. Regarding the full transition matrix, then there are two considerations. One of them is the runtime, and the other one is the information, and both of them are important. I think that it is somewhat more difficult to learn the transition matrix than to learn the phis, probably due to the sparseness. I'm not sure if that's an idea that I have, but I'm not sure about it. Well, anyway, we're experimenting with it, so I can't give you a really good answer. That was the reason why we did it this way, but I will be able to give you a good answer only after we finish experimenting with this and I see the results.
Any more questions?
Maybe someone in New York has a question.
Did New York end up connecting? I don't know. No. Okay.
They're not connected.
In that case, let's thank our speaker.